Hello everyone, my name is Brian Huck and today I'm going to talk about a max flow optimization problem through a bilevel network. The data that motivated my project was the open source Clark County data set. It consists of a lot of data on different networks such as human networks, communication networks, but I'm looking at the water network and the power network. And my actual problem doesn't use the real data because it becomes pretty complex. But I did model the two networks as a max flow problem, and I evaluated the individual networks, I connected the networks, and I did a basic sensitivity analysis and solved the problem in GAMS. So looking at the first network we have here, so the power network, it consists of a steam plant that generates electricity, sends the power to a distribution center, which then sends it to demand nodes. So it could be residential areas, hospitals, businesses, and so on. And to solve this as a max flow problem, we're going to push as much flow or power through the network to see how much it can handle, subject to upper level limit constraints on the arcs. And we're going to arbitrarily choose 20 and 10 for the arcs, and we do this by adding source and sink nodes. For our water network, we have a series of wells that pull water out of the aquifer, sends the water to a water plant to be cleaned and processed, which again meets demand of hospitals and residents and so on. And we solve the max flow problem by pushing as much water flow through the network to see how much it can handle, subject to the upper level limit constraints on the arcs, and we do this by adding source and sink nodes. So we have our two networks here. Now, we could optimize each network by itself, but to more closely represent the real world, we do know that when the water plant is cleaning the water and generating it, it needs electricity to do that. So we're going to connect the network, and we're going to say that water plant arbitrarily has a demand of 10 units of power. And we're going to do the same thing for the steam plant. We're going to say that the steam plant, to generate electricity, realistically needs that water, therefore it should be connected to the water network. But we're also going to add an additional assumption that the amount of water coming out of, or the amount of flow coming out of the water plant, we can see it, the upper level limit constraint is 8. But we're going to assume that it's proportional to the amount of power demand that is being met at the water plant. So it's demanding 10 units of power. If we don't meet that 10 units of power, then the amount of total flow that can come out of it will decrease proportionally to the demand that we did not meet. And the same thing can be said about the steam plant. Upper level limit of 20. If we don't meet its water demand, then that upper level decreases proportionally. So before we solve the problem, we're going to go over our notation. So as in traditional networks theory, we have a network G that consists of a set of nodes N and a set of arcs A, and the nodes are indexed on I and J. We have a supply and demand, so that's represented by BI, where if BI is positive, then it's a supply coming out of a node, and if it's negative, then it is demand going into a node. And each arc has a characteristic of an upper level constraint to it, represented by U sub ij. So the upper level limit going from node I to node J. And for our problem, our decision variable is going to be x sub ij. So the amount of flow that can go across or go from node I to node J. It's a continuous non-negative variable. So our formulation here to solve the max flow problem. So we're maximizing on V. So we're pushing as much flow into the network to see how much can actually come out of it. And we're going to push as much as possible. Our first constraint, x sub ij, so that's the amount of flow coming out of node I minus the amount of flow going into node I. So xji is the amount of flow going into node I. So this is our flow balance constraint. And considering only the source node, only flow is coming out of it. So since there's only flow coming out of it, then that flow balance is going to equal V. For all the other nodes that are not the source and sink nodes, so all the transshipment nodes, the flow in is going to equal the flow out, so that difference is going to equal 0. And for the sink node, there's only flow going into it, so it's going to equal negative V. X sub ij being less than U sub ij is just the amount of flow has to be less than or equal to the upper level limit on that arc. and then x sub ij greater than or equal to 0 is just that our decision variable is non-negative continuous. Now I did mention earlier about the assumption that the flow coming out of the water plant and the flow coming out of the power plant are proportional to the demand that is being met, and that's what this constraint is doing. So the demand for commodity K at node I is d sub I, and the amount of that commodity flowing into the node, I should have a superscript K there to match, but the upper limit coming out of the power plant and the water plant is going to be proportional to the ratio of the demand that is being met. Alright, so back to our problem. To solve these as individual network flow problems, max flow problems, we have to connect all the nodes to the sinks. And when we do that, we can see that we send 20 units of flow of power across the power network. And we can easily see that when we solve the max flow problem for the water network, we could send 18 units of water across the water network. Alright, so now it's going to start getting interesting. So we're going to decrease the upper level limit of the amount of power that can go to the water plant. And I just did this manually in GAMS, but this could represent anything. So let's say a malicious hacker of some sort hacks into our network and affects the ability to send power across our power grid. It could also represent a mid-level manager that reallocates resources and doesn't give that ARC the resources it needs to maintain the ability for that upper level limit. So whatever reason it is, we're going to manually adjust the upper level limit on that ARC, maintain the amount of demand at the water plant. So now the demand is not being met, when typically the amount of flow that could flow out of the power plant is 8. The demand is not being met, and we're actually missing it by 10%, so that 8 decreases by 10%, and we actually only get 7.2 units of water coming out of the water plant. So it negatively impacts the max flow reaching our sink node. And if we do the same thing for the steam plant, for whatever reason, the max limit going from the northern well transferring water to the steam plant decreases from 10 to 9, but the demand of water is maintained at 10. So we're missing that 10 units of demand, we're missing it by 10%, meaning that 20 decreases by 20%. The upper level limit decreases by 10%. Correction, sorry about that. And the overall flow reaching our power sink node is 18. So if we optimize the power network, we can get 18 no matter what decision we send out of the distribution node. So we could send 9 to the demand and 9 to the power plant, or 10 to the demand and 8 down to the water plant. We're still going to get 18 at the sink node. But this is an important point though, because if we optimize only on the network, only on the power network, it's not the same thing as optimizing on the bi-level network. Now, when we do this scenario in GAMS and we optimize for both networks, we will see that 10 units of flow get sent down to the water plant and 8 units of power flow go over to the demand node. And when we do that, we get a total amount of flow going through both networks equal to 35. So this is pretty important because optimizing on a single network, we could see, is not the same as optimizing on the bi-level network. There are cases in which maybe the demand might take priority, but that's a policy decision, and that could be manually input into a model. But I think the important takeaway though is that we might have a manager overlooking the power network, or we might have individual managers just looking at the water network, but it is important that they be looked at as a connected network because they do affect one another. And that's the key takeaway of this project. Optimizing on a single network is not the same as optimizing on the bi-level network. For the sake of completeness, here's my GAMS code. I broke it up between the water network and the power network. I didn't mention in the formulation because I wanted to keep it simple, but I do have 2 different decision variables, and then having 2 different flows being sent across the network. allows us to see which one are the max flows on each network, the individual network, and here is the code for our constraints. Thank you.